Remember the least squares assumptions for cross-sectional data? I'm thinking about the assumption 2, in which the x variable is independently and identically distributed across the sample. For example, you have the cross-sectional data like this. Okay, so you have x1, x2, and so on. And all these x's, these are independent, okay? So there's no correlation between any of these rows, okay? What if we have panel data? In panel data, we have entity, and we have time, but what if we distribute the x time, or entity 1, or let me do this in a different way. Let's say this is entity 1, right? Then we have x of entity I for time period 1 here, and we have x I time period 2, right? And x I time period 3. So the I stands for the entity, and the time period is here, 1, 2, 3, right? So what you see is that you have number x1, 1 here, you have entity 2 here, entity 3, right? And which means that here you have x2 period 1, x3 period 1. And what what assumption 2 in panel data says, it says that these xi's, or these x variables, they are independent when you look at different entities, right? But if you look at the within entity data, for example, these 3 x variables, they are allowed to be dependent. So these are allowed to be dependent, okay? Whereas the x variables within or among entities, they are not allowed to be dependent. This dependency of the x variable is probably more tangible by example. Okay, so suppose that for a given state I, which is the entity, okay, so this is entity, the beer tax in 1982 is correlated with the beer tax rate in 1983. So the beer tax is the x variable, and this is the time stamp. Okay, so sorry. What you do is that you look at the beer tax and you look at the time, and here you have 1982, here you have 1983, and so on, okay? What you might find is that the beer tax in all the 48 states, they are maybe something like this, some really high, some really low. This is just high, this is low, okay, low beer tax. So you have this distribution, right? And you can make this distribution in all of the time periods. But what if you look at one state? Okay, so this state has, okay, maybe here, the beer tax in 1982 is quite high, and the probability of this beer tax to be high in the next period as well is quite high in itself. So what you might see is something like this. If a state has a high beer tax in one period, the probability of the beer tax being high in that state the next period is quite high in itself. And low beer taxes follow low beer taxes, which means that the beer tax is correlated within the entity, within the state. Then we call it autocorrelation, or we call the beer tax to be autocorrelated or serial correlation. Let's not forget the residuals, the UIT, IT, because we look at both the entity and the time dimension. And as with the x variable, we might entity, okay, and we might collect the residuals. So we have UI1 here for the first time period, and the residual for the second time period, and the residual for the third time period, and so on. And if we have entity 1 here, then this number would be U11, and this would be U12, and likewise for the third year of residuals. Okay, so we might have in our model correlated errors, right? So if we follow our example, then our y variable, its fatality rate, and we try to explain the fatality rate by looking at the beer tax, one of the x variables, and we have created some other x variables, which are the state and time fixed effects, right? So these state and time fixed effects, they affect the intercept of our regression. But that might not be enough to explain our y variable, the fatality rate. So something else could be making the error that we are getting from the regression to be serially correlated, which means that the U11 is correlated with U12 and so on. So within the entity, we might have some serial correlation, but among entities, if you look at the vertical dimension, then you should not have any dependency or autocorrelation. So what might be a factor creating this dependency? Well, looking at fatality rates, then you might think that quality of road has something to say on the fatality rate. So worse roads, then fatality might increase, right? So and roads, they are not repaired at random. They are probably getting worse and worse and worse until they suddenly one year become refurbished and become better quality, which means that you have this correlation or autocorrelation in the state of the road because it's a bad road is probably bad or worse the next year as well. So why is this important? It's important because when we looked at the cross-sectional data with the OLS regression, we saw that either we have heteroscedasticity or homoscedasticity, and if we use ordinary standard errors, we assume homoscedasticity, but if we have heteroscedasticity in our data, or in our regression, I should say, then we could use something called heteroscedasticity robust standard errors. But these standard errors, even though they are called robust, they do not handle serial correlation. So because of this, we need something else to calculate our standard errors. And this something else is heteroscedasticity and autocorrelation consistent standard errors, or just HAC standard errors. And one type of this is called clustered standard errors. And this is because clustered standard errors allow for heteroscedasticity and serial correlation within an entity, okay? But it's important that across entities, we do not have this serial correlation. The good thing about clustered standard errors is that they give you the correct standard errors to use, which means that if you get a sample or a beta hat from a sample, then you can create the correct confidence interval, 95%, for example, confidence interval. Okay, so, and the good thing about the clustered standard errors is that you don't care about heteroscedasticity or serially correlated X or residuals, right? And it's easy to use. So in Stata, we just add the term cluster in the panel data regression.